Hey everyone, and welcome to your ultimate masterclass on metals and nonmetals. If you're gearing up for your Class 10 CBSE Science Board exams, you are in the exact right place. Today, we're going to distill this massive, detail-heavy chapter into high-yield, step-by-step concepts to help you score maximum marks. I'm going to walk you through not just the what, but the why behind every chemical reaction and property, exactly the way an experienced examiner wants to see it on your answer sheet.
Here's our game plan for this explainer. We'll hit 1. Properties and exceptions, 2. Chemical reactions, 3. The reactivity series, 4. Ionic bonds and extraction, 5. Corrosion and alloys, and wrap up with 6. A rapid revision sprint.
All right, let's jump right into Section 1, Properties and Hidden Exceptions. Now, examiners rarely ask you to list basic properties. Instead, they absolutely love to trick you with the exceptions. We all know metals are generally hard solids with high melting points, right? But here is an insider tip for you. Alkali metals, like lithium, sodium, and potassium, are actually so soft you can literally cut them with a butter knife. And while most metals need massive heat to melt, gallium and cesium have incredibly low melting points. Seriously, if you place a piece of solid gallium on your palm, your body heat alone is enough to melt it into a puddle. Oh, and never forget mercury, the only metal that's liquid at room temperature. Let's test your knowledge real quick with a concept checkpoint. Nonmetals are supposed to be dull insulators, right? So can you predict which nonmetals actually break the rules and act like metals by conducting electricity or having a shiny surface?
Well, if you guessed graphite and iodine, you are spot on. Graphite is an allotrope of carbon, so it's just carbon atoms, but they're arranged in a way that lets it conduct electricity perfectly. Iodine, on the other hand, has this beautiful metallic luster, even though it is a pure nonmetal. And just like mercury is our liquid metal exception, bromine is our sole liquid nonmetal exception. Make sure you memorize these three because they are super frequent one-mark questions.
Moving right along to Section 2, Chemical Reactions Unlocked. Let's dig into the deep reasoning behind how these elements behave chemically, so you aren't just memorizing, but actually understanding. Now, most metal oxides are strictly basic, but a few of them like to play both sides of the field. Amphoteric oxides, specifically aluminium oxide and zinc oxide, can react with both acids and bases to produce salt and water. Guys, this is a guaranteed high-probability board exam topic. Understanding that they act as an acid when facing a strong base, and as a base when facing a strong acid, is absolutely key to writing out those tricky, balanced equations. But before we reveal all the reaction mechanics, let's do a mini quiz. What do you think happens when we expose different metals to water? Like, does a piece of sodium in cold water react the exact same way as a piece of magnesium in hot water? The secret here lies in their varying reactivity. Sodium and potassium are so violently reactive that they catch fire in cold water instantly. The reaction is highly exothermic, which actually ignites the evolved hydrogen gas. That's exactly why we have to store them totally immersed in kerosene oil. Magnesium, however, is a bit more chill. It won't react with cold water, but it will react with hot water. And here's a great memory trick for you. Magnesium floats because the hydrogen gas bubbles produced actually stick to the metal's surface. It's like they're wearing tiny life jackets. Meanwhile, tough metals like iron and aluminum won't even look at liquid water. They strictly require high-energy steam to react at all, and they form metal oxides instead of hydroxides. Which brings us perfectly to Section 3, Reactivity and Displacement Reactions. So clearly, not all metals are created equal, and that's the whole logic behind the Reactivity Series. Memorizing this hierarchy is literally your secret cheat code for the chemistry section of your board exam. At the very top, we've got the highly reactive kings, potassium and sodium. In the middle are the moderately reactive metals like zinc, iron, and lead. And sitting at the very bottom, we find the noble, unreactive metals like silver and gold. That's exactly why we use them for jewelry. They just don't corrode or react easily. Knowing exactly who sits above whom on this list is non-negotiable. And why is that list so important? Because of the displacement rule. Simply put, a more reactive metal will always displace a less reactive metal from its salt solution. Think of it like this. If a strong, highly reactive metal meets a chemical compound of a weak metal, the strong metal essentially bullies the weak one, kicks it right out of the solution, and takes its place. The famous thermite reaction is a spectacular real-life example of this displacement. Aluminum sits higher on the reactivity series than iron, so when aluminum powder is mixed with iron oxide and heated up, aluminum violently displaces the iron.
This reaction is so intensely exothermic that the displaced iron is produced in a completely molten liquid state. We literally use this exact reaction right on the tracks to weld cracked railway lines back together.
Let's tackle Section 4, ionic bonds and extraction. Okay, let's get into the heavy 3 to 5 mark questions regarding how metals bond with nonmetals and how we actually extract pure metals out of the Earth's crust. When metals, which love to lose electrons, react with nonmetals, which love to gain electrons, they form ionic compounds. The metal becomes a positive ion, the nonmetal becomes a negative ion, and they lock together in a tight crystal lattice. Now, examiners will always ask why ionic compounds have such incredibly high melting and boiling points. The magic phrase you must write in your exam is this: due to the strong electrostatic force of attraction between the oppositely charged ions. You need a massive amount of heat energy to break those invisible, powerful bonds.
So, how does this tie into metal extraction? Well, for top-tier reactive metals like sodium or aluminum, traditional heating with carbon just won't work because these metals have a higher affinity for oxygen than carbon does. So we have to use a brute force method, electricity. In electrolytic reduction, we take the molten ore, like molten sodium chloride, and pass an electric current straight through it. The positively charged sodium ions migrate over to the negatively charged cathode and deposit as pure metal, while chlorine gas bubbles off at the anode. It's step-by-step, simple, and highly effective.
Let's zoom out a bit for Section 5, corrosion and useful alloys. Taking a step out of the lab, let's look at the practical applications and the natural consequences of metal reactivity in our daily lives. Corrosion is basically nature's way of reclaiming metals. When exposed to moist air over time, metals degrade. Iron rusts into a flicky brown powder, silver tarnishes black, and copper gets that green coating of basic copper carbonate. But humanity fights back by creating alloys. An alloy is a homogeneous mixture of two or more metals, or a metal and a nonmetal. By melting them together, we completely upgrade their properties. We take pure iron, mix it with a little carbon, chromium and nickel, and suddenly we have stainless steel. It's hard, it's strong, and it completely resists rusting.
And finally, Section 6, board exam rapid revision. Let's finish strong.
We are in the final sprint of this explainer. Let's cement the most expected questions and the exact chemical equations you absolutely need to memorize before walking into that exam hall. Here's a classic previous year question where 90% of students literally throw marks away. We learned earlier that metals react with acids to produce salt and hydrogen gas, right? So can you spot the trick here? Why is hydrogen gas not evolved when a metal like zinc reacts with nitric acid?
It's because nitric acid is the great exception. It is a remarkably strong oxidizing agent. As soon as the hydrogen gas is produced during the reaction, the nitric acid immediately oxidizes that hydrogen, turning it straight into water, while the nitric acid itself gets reduced into nitrogen oxides. The only two metals that bypass this rule and actually produce hydrogen with very dilute nitric acid are magnesium and manganese. Definitely note that down. All right, here is your final checklist. Make sure you review these 4 specific areas heavily tonight. You need to know the definition and examples of amphoteric oxides. You need the balanced equation for the thermite process used on railways. You need to be able to explain the reasoning for storing potassium in kerosene, and you must understand the setup for the electrolytic refining of impure copper. I promise you, these show up year after year. And speaking of amphoteric oxides, always write balanced equations in your answers. This exact equation, showing solid aluminum oxide acting as an acid reacting with aqueous sodium hydroxide to produce sodium aluminate and water, is an absolute goldmine for marks. Do yourself a favor and write it out 3 times today until it is pure muscle memory. I'll leave you with this final predictive thought to test your mastery of the displacement rule and the reactivity series. If you dip a silvery white zinc strip into a blue solution of copper sulfate, what exactly will you observe visually after 2 hours? Think about the color changes and what metal coats the strip. Good luck with your revision, keep visualizing the chemistry happening all around you, and you are absolutely going to crush this exam.